Hello and welcome back to Drilling Sessions. Today we're tackling an essential and fascinating topic – numerical systems. Numbers are everywhere in programming and computer science, and understanding numerical systems is key to unlocking many advanced concepts in coding and memory design. We'll start by exploring how numerical systems are created, dive into the most commonly used systems like binary, octal, hexadecimal, and decimal, and finish with how the binary system relates to computer memory. Let's get started. First, let's define what a numerical system is. A numerical system is simply a way of representing numbers using a consistent set of symbols. The numbers we use every day, 0, 1, 2, 3, and so on, are part of the decimal system, which is a base 10 system. It uses 10 symbols, 0 through 9. Every numerical system has the three main components. Base, or radix, is the total number of symbols used in the system. Symbols, the digits or characters that represent values, and positional notation. The position of each digit determines its value based on powers of the base. For example, in the decimal number 345, the rightmost digit 5 represents 5 multiplied by 10 in the power of 0, which is simply 5. The middle digit 4 represents 4 multiplied by 10 in the power of 1, which is 40, and the leftmost digit 3 represents 3 multiplied by 10 in the power of 2, which is 300. When you add them together, you get 345. But what if we want a system with fewer symbols, like just 2 or 8? Let's break down a few examples to show how numerical systems are built. Binary system, base 2, uses only 2 symbols, 0 and 1. Octal system, base 8, uses 8 symbols, 0 to 7. Hexadecimal system, base 16, uses 16 symbols, 0 to 9, and A to F, where A represents 10, B represents 11, and so on. Each of these systems follows the same positional notation rule. The position of a digit determines its value based on powers of the base. For example, in hexadecimal 3F, F represents 15 multiplied by 16 in the power of 0, which is 15. 3 represents 3 multiplied by 16 in the power of 1, which is 48. Adding them together gives us 63 in decimal. Beyond these systems, there are others, like base 3, ternary, which is used in some theoretical computing systems, or base 64, which is common in encoding data. Okay, but why? Why do we even need systems like octal or hexadecimal when we already have decimal? Well, it comes down to readability, efficiency, and context. Let's break it down. Binary is essential because computers operate at the hardware level using electrical signals that are either on, 1, or off, 0. It's the simplest system for hardware to process, but it's extremely tedious for humans to work with directly, especially for large numbers. For example, representing the decimal number 255 in binary requires 8 bits. Imagine working with even larger numbers. It's not very practical to debug or interpret. Octal historically gained popularity because it's more compact than binary and still relatively easy for humans to work with. In older systems, particularly early Unix systems, octal was used to simplify binary groupings. Each octal digit represents 3 binary bits. While octal is less common today, you might still encounter it in specialized areas like Unix file permissions, where shorter representation of binary data are needed. Hexadecimal is widely used in modern computing because it's the perfect middle ground between binary and human readability. Each hexadecimal digit represents 4 binary bits, so it's much easier to interpret and debug than binary. Hexadecimal is especially useful in areas like memory addresses, where hex makes long memory addresses manageable and readable, color codes. Hex values represent RGB colors compactly and are easier to read than binary, and machine code and debugging. Hex is commonly used to represent instructions and data at a low level, making it easier to read than pure binary. Decimal is intuitive for humans because it's the system we use in everyday life. While not as compact or directly tied to hardware as binary, decimal is still essential for interfaces, calculations, and outputs intended for human users. So, while binary is great for machines and decimal is natural for humans, systems like octal and hexadecimal make it easier to bridge the gap between the two. They allow programmers to interpret and represent binary data more efficiently without losing the connection to machine-level details. Each system has its place depending on the use case. Now, let's dive into conversions between numerical systems step by step. We'll start with decimal to binary conversion. To convert a decimal number to binary, repeatedly divide the number by 2 and write down the remainder. The binary number is the sequence of remainders, read from bottom to top. Let's convert 13 to binary. 13 divided by 2 is 6, remainder 1. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1, and 1 divided by 2 is 0, remainder 1. Reading the remainders from bottom to top gives us 1101. To convert binary to decimal, multiply each bit by 2 raised to the power of its position, starting from 0 on the right. Here is an example of converting 1101 from binary to decimal. For decimal to hexadecimal conversion, divide the decimal number by 16 and write down the remainder. Use symbols 8 to F for remainders above 9. Let's convert 255 to hexadecimal. 255 divided by 16 equals 15, remainder 15, which is F. 15 divided by 16 is 0, remainder 15, which is also F. Reading from bottom to top, 255 in decimal is FF in hexadecimal. Binary to hexadecimal is simple. Group the binary number into groups of 4 bits, starting from the right, and convert each group to its hexadecimal equivalent. Finally, let's talk about how the binary system is used in computer memory. Binary numeric system is used to represent all types of data, whether it's numbers, text, or even images. For example, integers stored as binary numbers, characters represented using encoding schemes like ASCII, where each character is assigned a binary code. Colors are often represented in hexadecimal for convenience, but ultimately they're stored in binary. But again, why? Because when we store something in memory, we always reach the hardware side of this. A computer's most basic building block is the transistor, a tiny electronic switch that can be either on or off, representing the two binary states, 1 and 0. This simplicity makes binary the most natural way to process and store data in electronic systems. That's all for today's video on numerical systems. We've explored how numerical systems are created, the most common ones in use, and how to convert between them. Understanding these systems is fundamental to working with low-level code and computer memory. Thanks for watching and happy coding!